Hello everyone, my name is Victran. In this video, I will be presenting about the methodology of evapotranspiration and soil moisture submodels of ETLook. First, I will explain the ETLook methodology to calculate reference evapotranspiration RET, then the actual evapotranspiration and interception AETI, and finally the relative root zone soil moisture. RET is calculated using Penman-Monteith equation standardized in the FAO 56 report, without separating evaporation from soil and transpiration from the canopy. The reference crop parameters are defined in the FAO 56 report, including crop height, bulk surface resistance, and albedo. ETLook models use data from global climate model or reanalysis such as GOS5 and ERA5 to derive meteorological variables including vapor pressure deficit, air temperature, wind speed, psychrometric constant, and the slope of the saturated vapor pressure curve. Net radiation is calculated using the radiation balance equation, where the solar radiation, albedo, and net long-wave radiation are derived from the satellite data and global climate model input. I will explain the ETLook methodology to calculate reference evapotranspiration RET, then the actual evapotranspiration and interception AETI, and finally the relative root zone soil moisture. ETLook model calculate actual evapotranspiration and interception AETI independently from RET. The model first calculates soil evaporation, canopy transpiration, and interception, then sum these three components to calculate total AETI. Interception is a function of vegetation cover based on normalized difference vegetation index, leaf area index, and precipitations as follows. All these three inputs are derived from satellite data. For evaporation and transpiration, two versions of the Penman-Monteith equation for soil and vegetation are used respectively. The meteorological variables are calculated the same way as in reference evapotranspiration method. The main differences are how net radiation, soil heat flux, surface resistance, and canopy resistance are calculated. For evaporation and transpiration, net radiation is calculated using the radiation balance, subtracted the energy needed for interception. Furthermore, net radiation is separated into soil net radiation and canopy net radiation by a function of LAI and land cover specific light extinction factor. Soil heat flux is calculated to estimate net energy availability for soil evaporation. For transpiration equation, the soil heat flux is not considered. ETLook used formula detail in FAO 56 report where soil fraction is derived from LAI and yearly air temperature amplitude is derived from daily air temperature. Soil thermal conductivity is a function of relative soil moisture content, and damping depth is derived from soil thermal conductivity and volumetric heat capacity, which is also a function of relative soil moisture content. As we can see, LAI, air temperature, and relative soil moisture content are the key data inputs to calculate soil heat flux. The next variables to calculate in Penman-Monteith equation is surface resistance. Soil surface resistance in soil evaporation equation is modeled using a constant power function of relative soil moisture content as follows. The minimal soil resistance is a default value of 800 seconds per meter. Similar to soil heat flux method, relative soil moisture content is the output of root zone soil moisture model. The canopy surface resistance is more complicated to calculate as it depends on effective LAI, minimal stomata resistance, and multiple stress factors according to the Jarvis-Stewart model. In ETLook, The minimal stomata resistance is predetermined by land cover. Temperature stress is a function of air temperature. Vapor pressure stress is a function of vapor pressure deficits. Both are derived from climatic data input. Radiation stress is a function of incoming shortwave radiation, which is derived from the solar radiation data input. Finally, the soil moisture stress is calculated from relative soil moisture content. The aerodynamic resistance in Penman-Monteith equations are calculated for both neutral and non-neutral conditions. Neutral condition exists when turbulence is caused only by shear stress or wind, using the classical formula. In ETLook model, the soil and canopy surface roughness are estimated from land cover, obstacle height, and orographic roughness, which is a function of digital elevation model, DEM. The approach is to assign maximum obstacle height from which surface roughness and displacement height are derived. In addition, NDVI is used to adjust the obstacle height according to seasonal variation of vegetation. Non-neutral conditions are caused by buoyancy or thermal rise of air. The effect is described by the Monin-Obuchov similarity theory by means of stability corrections. These stability corrections for heat is a function of obstacle height, displacement height, and Monin-Obuchov length. Since the sensible heat flux is an unknown required to estimate Monin-Obuchov length L, and it is the difference between available energy and latent heat flux, an iterative process is applied in ETLook model to solve for non-neutral condition. First, the initial estimates of aerodynamic resistance are calculated using neutral condition formula to estimate transpiration and evaporation. Then, sensible heat flux of canopy and soil are estimated using surface energy balance, which are then used to estimate the Monin-Obuchov length and stability corrections. Next, the stability corrections are used in the non-neutral formulas for aerodynamic resistance. The new estimates of aerodynamic resistance are compared to the earlier estimate. Until both estimates converge, the final estimates of transpiration and evaporation are calculated. I will explain the ETLook methodology to calculate reference evapotranspiration (RET), then the actual evapotranspiration and interception (AETI), and finally the relative root zone soil moisture. Next, we will look at the methodology of the relative root zone soil moisture model. The model is based on the linear correlation between land surface temperature LST and vegetation cover, which is derived from NDVI, for specific relative soil moisture content as described in the paper by Yang et al. In 2015. This is called trapezoidal method. The top light segment of the trapezoid from AB shows the LST vegetation cover relationship under completely dry conditions. As you can see, relative soil moisture content is equal 0. The bottom line segment DC represents soil moisture at field capacity, which means relative soil moisture content is 1. Point A and D represent bare soil, while point B and C represent full vegetation cover. The trapezoid corners A, B, C, D are determined for each pixel by estimating the minimum and maximum temperature of soil and canopy as following. The linear relationship between LST and vegetation factor is described by the soil wetness isolines for each value of relative soil moisture content. With this linear relationship, the model calculates relative soil moisture content for a specific point using the actual LST and vegetation cover values from satellite data. This model allows generating relative soil moisture content input for evapotranspiration and biomass models, at the time of overpass and spatial resolution of LSC and NDVI satellite data input. It also indicates better the water content in the root zone in the subsoil than microwave satellite methods, which are only able to observe soil moisture content in the top few centimeters of the soil layers. I will explain the ETLook methodology to calculate reference evapotranspiration (RET), then the actual evapotranspiration and interception (AETI), and finally the relative root zone soil moisture. We have covered the fundamental methodology of evapotranspiration and root zone soil moisture models. As you can see, satellite data and climatic data are used many times in ETLook model to estimate several intermediate and ultimate outputs. Therefore, the accuracy of model inputs and functions are very important for the quality of Vapor data products. To know more detailed derivation of all variables and parameters in ETLook model, you can refer to the Vapor methodology wiki page.